Okay, so we're just going to finish up here on these last couple of topics, percent composition, percent yield, and empirical formula. And you really need to go back and watch the videos on these if you have not already. I'm just going to give you a brief overview, okay? So percent composition, it is something that has to be in grams, okay? You can't do the problem if it's in moles or liters, so you always want to convert it to grams using our mole ratios that we learned in Chapter 10. And what the basic equation is it's grams of a element over grams of a compound. Okay. Okay, and so we can take this from a balanced chemical equation. We can take this just from given information in the problem. I'm going to write out the chemical equation. Okay, this is one we did in lab, magnesium oxide. So it might give you any set of information, but you need to have all three of these in grams. Or if there's two products, you need to have all four. Okay. So if let's just say we weighed out 2 grams of magnesium and we ended up with 7 grams of magnesium. Okay. So these are what you did in lab. So we could calculate how much oxygen we had here just by subtracting, obviously. So we have 5 grams of oxygen that we must have obtained from the air. Okay, so now we would just want to take and we'd want to see the percent composition of this element within this. Okay, so we get 2 grams of the magnesium, and we have 7 grams of the magnesium oxide. Okay, and we would go ahead and we would divide this. Do that. 2 divided by 7 gives us 0.28. Times that by 100, and we would get 28% magnesium. And then the other one, 5 grams of oxygen over 7.0 grams of magnesium oxide. We do 5 divided by 7, and we get 71, or 0.71, times 100, and we get 71%, and that's oxygen, and this is magnesium. Okay, and one thing to note here, you do want this to add up to 100. So I obviously had a little bit of a rounding error here. This was 0.7148, so this would actually be 72. So if we added that up, it would equal 100% of the product. Okay. Now percent yield is a little different. What we're talking about here, we can use the same thing of information. I'm just going to use this for percent yield as well. Now we're going to see, okay, so this is what we got in lab. This might be your lab results, but percent yield is calculating what it should have been, okay, using the mole. So here you're using moles, okay, which is a little different because in this one you use grams. So here we might say we have 2 grams of magnesium, and what we need to do is we need to find magnesium's molar mass, so we can do 24.3051 grams of magnesium over 1 mole of magnesium. And we use this mole ratio. Okay, we're going to magnesium oxide. This is always for a product, moles, and it's important. And then you're always looking at the product, the solid product. Okay, so you'd have 1 mole of magnesium. And I better balance this chemical equation here. So we actually have 2 moles of magnesium over the 2 moles of magnesium oxide. And then you have 1 mole of magnesium oxide over its molar mass, which would be 24 plus 15, 24.3 plus 15.9999, which would give us 40. Where's my cursor? Okay, 40.3 grams. Okay, and so we take 2 divided by 24.305 equals, and then these 2's basically just cancel out because it'd be times 2 divided by 2, and then we would times this whole thing by 40.3, and we would get 3.32 grams of magnesium oxide. That's what we should have gotten. In a perfect reaction, if you started out with 2 grams of magnesium, we should have gotten 3.32 grams of magnesium. Now, obviously, we got 7, so we did something severely wrong. I didn't do a good job of making up that number. But what you would do is you would take your theoretical yield and you would just divide it by what you really got. So this is called your actual over your theoretical. Okay, so actual over theoretical. Okay, so this is theoretical, means you calculated it out. So we do 7 divided by 3.32 gives us 2. We already know this is going to be a disaster. We were really far off. So we got 210%, which is obviously we got way more than we should have. So we got water. We have something else that didn't work out here. You want to be close to 100, but you don't want to be over 100 because that means you made an error in a different way. Okay, so let's go over empirical formula here and molecular formula. All this is when you're not given the information. Molar mass is important in this, and really all you are doing is you're going to be calculating moles. Okay, so empirical formula, if you have a set of information, most of the time it'll be in percents. Okay, so earlier we calculated the 2% out for magnesium, 28 and 72. Okay, so you'll be given information something like this. Another example would be 74.1, or actually let me do one of your homework problems, that way you guys can check and see if you're right. The last homework problem, number 37, says 1,6-diaminohexane is used to make nylon. What's the empirical formula of this compound? And it says you have 62.1% carbon, 13.8% hydrogen, and 24.1% nitrogen. Okay, so this is what they make nylon out of. So what you would do is you would simply take these numbers and you would assume that they're grams out of 100, because this should add up to 100%. So we just say, oh, we have 62.1 grams of carbon. We have 13.8 grams of hydrogen, because everything has to be in grams in this one too. 24.1 grams of nitrogen. And what you're going to do with these numbers is you are going to take it by their molar mass. So we're going to get moles of each of them. So you take molar mass is important because you go from percent to grams to moles. Okay, and that's all we're doing. So we take 62.1 grams of carbon, and we do grams of carbon on bottom, so we do 12.001, 1 mole of carbon. So you take 62 divided by 12, and we get 5.175 moles of carbon. Take the next one, 13.8 grams of hydrogen, put hydrogen on bottom. 795 grams of hydrogen, 1 mole of hydrogen. So you get 13.8 divided by 1.00795, and we get 13.69 moles of hydrogen. And then our last one is 24.1 grams of nitrogen. Grams of nitrogen goes on bottom. We know that's 14.0067, 1 mole of nitrogen on top. So we get 24.1 divided by 14.007, and we get 1.72 moles of nitrogen. Now we look at which one of these is the smallest. Whatever one is the smallest, that's what you divide all of them by. So 1.2 or 1.72 is the smallest, so I divide them all by that. So you get 5.175, and sig figs are really important in this, okay? And this one would be somewhere right around 3. So we do C3, okay? Then 13.69 divided by 1.72, we get 7.9. So I'm going to go ahead and round that up to a 9. So it's going to say H9. And then nitrogen is my last one, which is a 1-to-1 ratio, obviously. So it's just going to be N. Okay? Now, that is your empirical formula. Okay? So if they told you that your molar mass was, let's say, around let's say around 141. Let's say it tells you that. Okay? Molar mass is equal to 141, or around that. Okay? So if we calculated this molar mass, so we do 12 times 3 equal 36, plus 9 hydrogen, plus 14 for the nitrogen, we get around 59. Okay? So this molar mass is around 59, 60. So how could we get to 141? So you take that 59 times 2 would be 118. 59 times 3 would be 177. 59 times 3. Okay, that was supposed to be 81. Sorry. And it gives you 81. We would know that we had to take all of these numbers times 3 in order to match that molar mass. When you match molar mass, that becomes your molecular formula. So then it would be C times, or 3 times 3, which would be 9, and then 9 times 3, which would be 27, and then we would have 3 nitrogen. Okay? And so this would be our molecular formula after we looked at our molar mass. Okay? So make sure you look over any of the videos that you don't understand tonight, and I'll be here in the morning if you want to ask questions. Good luck on your final. Okay? Have a good night.